Oh, nice. So many pop-ups. Okay, yeah, so this is joint work with Irit and Siki. Cool. I'll use this.
Oh, if you click on you want to click on your slide and then.
Okay. Where's my mouse? Okay.
Yeah, there.
Cool.
Now I think.
Okay, so I guess the type of codes that I'm going to be talking about today are codes that are locally testable. So maybe let me tell you what that is. So maybe before we get to local testability, let's talk about just codes. So linear code we can think of as a linear subspace of maybe the n-bit space. And there's sort of two main metrics that people are interested in for codes. The first is rate, which is sort of like how many bits of information are you actually encoding? So the dimension of your space over the length of your code words. And the second metric is distance, which is sort of like the minimum distance between, in Hamming distance between any two code words. So ideally, you want the rate to be large, close to 1 as possible, but for us, positive is going to be enough, like positive constant. Distance, you want to be also as large as possible. For us, I guess positive constant is also going to be what we're aiming for. Okay, so local testability is the following property. It says that if you are given a code word, you can test by reading a few randomized bits whether or not this code word is in as close to your code, right? Or as close to your code space. So of course you can't test exactly. If there's one bit that's changed from your code space, then of course you can't necessarily detect it, right? Because you're only given a few places you can only check a few places. So I guess here's the properties you want. So first, if your word is actually in your code space, then you should always accept. And second is if it's not in the code space, you should reject as probably sort of scaling with the distance to the code. So if one bit is changed, you can't detect it, but if many bits are changed, you should be able to detect with pretty high probability.
Just have a notation delta is normalized for you, or
what did I do? Yeah, I guess these things, I often confuse these things. I guess usually it's not normalized. So maybe I should have said positive constant times n. So yeah, thank you. Okay, any questions? This is going to be object. Okay, so maybe let me give you some history on this topic. So why do people care about LTCs? Well, the reason these things come from sort of study of PCPs in the 1990s. And maybe so LTCs are often used in constructions of PCPs. I think in all the algebraic constructions that I know, there's some LTC as the backbone of their PCP. And I guess maybe another way to sort of see intuitively why these things are very related is as follows. So a PCP, you're checking sort of closeness to a correct proof. LTCs, you're checking the distance to a code word or a code space. So sometimes these things are very related. And so through the study of PCPs, they were constructing better PCPs. One major component of doing so was to construct better LTCs. And so the best LTCs that were constructed through this process have rate 1 over polylog, and then constant distance to locality. I guess I'm talking about relative distance here. Yeah, and so then there's this big question.
What is locality?
Locality is the number of queries you're using for testing. Yeah, thank you. See how this works. Okay, so there's a major question, which is what is the best possible parameters for an LTC you can get, right? If you want better PCPs, you need better LTCs. Can we get best parameters on all of these 3 categories that I told you? So critically the question was, can you get these C-cubed LTCs? So can you get constant rate, constant distance, and constant locality? Okay, and this question, people didn't make progress on this question for about 10 years following these works. But then people were okay, maybe we can drop the applications of PCPs and just try to construct these things in themselves. And they were able to construct LTCs with constant distance and rate. But now the locality has blown up to, I guess, log n to the log n. So these things actually are not applicable for PCPs. They are sort of constructed using expanders. Yeah. Okay, and then it's okay, can you improve these things? Can you get both constant in all 3 categories? And there's a framework that's proposed to do so. So there's been a lot of recent interest in these high dimensional expanders in the TCS community. And I guess it's proposed. Okay, so people notice. Okay, there's this sort of these HDXs kind of gives us local to global phenomenon, where if you can show, I guess some local testability sort of at a base code, then you can get local testability everywhere. And sort of, I guess these 3 works showed this thing. And then I guess the question is like, can you find this compatible base code? Can you like instantiate this base code, and then from that you can get the entire, a big locally testable code. And it turns out this was kind of hard. People tried, couldn't analyze it. And so a couple of years ago, there was a big breakthrough that actually constructed C-cubed LTCs. But what they did was they like departed from the HDX framework. They constructed these new kind of expanders that where the base codes of the top faces are sort of like these squares, which are easier to analyze. These are called left-right Cayley complexes. And using these things and using, I guess, like existing analysis of like these things called tensor codes, they were able to construct C-cubed LTCs. So I guess I wanted to mention like everything on the right there are codes that are sort of like this like LTC question. They don't really have like applications to PCPs. They don't have any like additional structure that would be useful for PCPs. So I guess, we'd like to come back to the question of can we construct LTCs kind of compatible with PCPs? What are the best parameters we can get? So, okay, so what do we do in our work? So our work is the following. We kind of go back to this HDX framework for getting LTCs. And we instantiate it with some base code that I'll tell you about later that is compatible with these HDXs and I guess like have this sort of additional property that might be useful for PCPs. That's what we did.
So what is the hope for PCP?
Was the hope for PCP like was a big question there? Or
if we have better LTC then?
Yeah, so I guess like maybe like one big question in like PCPs is like, can you get PCPs with like linear size? So right now like the best PCPs are like n to the 1 plus like little o of 1, but the hope is you get rid of little o of 1, for instance, and for that you'd need better LTCs. Like you'd want really like constant rate, constant distance. Maybe locality doesn't matter quite as much, but yeah.
So what's the additional like property that you need for?
Yeah. So it's like a property called the multiplication property. It says basically if you have two code words, you take the pointwise product, you get a new code word and like a related code. So this is true for like Reed-Solomon or Reed-Muller, if you know what these are.
And that's the property you need for the PCPs, like for the gray area.
Yeah.
That they need to be multiplicative, like pointwise.
Yeah.
multiplicative.
Yeah, or we know how to go to PCPs if you have this plus like some check protocol or some sort of like protocol is consistent with these codes.
Okay. Yeah.
Okay. So our result, so we instantiate a specific HDX called the Kaufman and Oppenheim HDX with a compatible base code. So our main contribution, I guess, is analysis of this compatible base code. And I guess I want to say that our construction gets constant distance and locality. And we know there's many code words, but like we couldn't show that the rate was, I guess, positive constant. So there's some work to be done there. Like the hope is like if you could tighten the analysis, maybe you can show positive constant rate, and then we could get a new family of C-cubed LTCs that also have this sort of multiplication property, which would be very interesting. Okay.
So what is the rate you have?
I don't know, maybe it's like, I have to get back to you on that. I forget if it's like 1 over polylog or if it's like the total number is like some exponential, I forget.
But it's still n to the small of 1, yes, or n to the minus a small of 1. Or...
Yeah. It's less than, it's not constant. Or not like proportional to the the rate is sub sub constant.
It's not like sub-polynomial also. Or square root n.
So I guess it's like at least as good as like what Reed-Muller gives you. Okay, so I guess like why do people? So I guess the question is like why? So I guess there's two sort of main benefits I see of this result. The first one is that we get this multiplication property, which is what as I said, you take two code words, and if you pointwise multiply them, then you get a new code word and related code. And this will hope to give you PCPs. The second property I think is kind of nice is that these like left-right Cayley complexes, like there's really just a two-dimensional structure. Like you can't really, at least we don't know how to generalize it to higher dimensions. But for certain applications, such as for quantum LTC, you would actually hope to have like a code on a higher dimensional chain complex. And ours would be compatible with that. And so there's some hope, like maybe by using similar techniques, you can actually get results for applications such as quantum LTC. Okay. So Okay, so maybe let me tell you what I'm going to tell you today. So I guess I want to start pretty basic. I want to tell you about sort of expanders and codes. And then I want to tell you about like HDXs and codes and sort of why if you have a compatible base code, you can kind of get this local to global phenomenon for local testability. And then I'm going to tell you very briefly about the base code that we're using. And then, yeah. Okay, so I guess let's start with expanders. So what are expanders? Expanders are sort of like sparsified complete graphs, but they should have similar sort of expansion properties. So in particular, we can consider like D regular graphs where D is a constant. And I guess small space should expand, so there shouldn't be like any component that's kind of disconnected from the rest of the graph. It should all be very connected. Okay, so how do you define a code on these things? So we're going to put bits on the edges. So if there's n edges, there should be n bits. And for every vertex, there's going to be sort of like a constraint imposed on the surrounding edges. So in particular, so at every vertex, if you look at the edges surrounding it, then these bits should like belong to some base code called C base. Okay, and I guess in some sense, like this sort of setup kind of suggests the following local test. Like maybe you're trying to test if this is a good code word. Already you have sort of this constant like degree at each vertex, right? So it suggests the following local test. What if you pick a random vertex and then you check if the local view at that vertex is in the base code? And this seems like a pretty reasonable test, right? Because there's like, I guess, constantly many edges surrounding each bit, so it's constant locality. I guess the question is this test robust? What do you guys think? Okay.
So for it to be robust, you needed the big code to be collection of bunch of small codes, but also like you cannot have a code that has lots of a small code. Sorry, you should not have a string that has lots of base code inside it, but it's not a code itself. Yeah.
Yeah. Yeah, so I guess you want it to be the case that if most vertexes like the bits surrounding it are in the base code, then you don't want there to be such a word if it's not actually in the base code. It's not actually in the code. Yeah. Okay. So actually it turns out that for generic expanders, this test is maybe not so good. Let's see why. So maybe we can take a vertex and we can remove the constraints there. Now this defines a bigger code, right? Because you have one fewer constraint and same number of edges. And yeah, and so maybe you can find a code word that's in this larger code space, but it's not in the original code space. Now, if you pick a random vertex, except for that one you deleted, it should satisfy the check, right? But now you actually have distance from the original code space. You're in this larger code space.
But your distance is not too high, right? Because now you're only changing, let's say, like a constant number of bits. So if you, by the expansion, we would expect that if you change a lot of bits, then, I mean, a lot of these edges are going to be.
Yeah, I think maybe the better way to think about it is, so originally you have some code space defined by all these vertex checks, right? So it's something dimensional space. Now you're removing the checks at a single vertex. And now you've like removed several constraints. So now your space is actually like, several times bigger. And now so now your lattice is like bigger. And now you can find a point that's in this new lattice, but it's not in your old one. And now it's actually kind of far away from your old lattice. As you can imagine, this should be the case for a generic expander.
Okay.
Distance is just having distance.
Oh, yeah. Yeah, so it turns out this test is not robust for that reason. So like you would actually probably want some like additional structure. I guess the issue here is that these expanders are very like unstructured. They could really be like anything. You don't really have control over what this like new code once you delete a single vertex looks like. So you really need some more structure to be imposed on this graph in order for it, I guess, to be a good to hopefully give you a good code.
Just want to make sure I understand, I have the right mental picture. So the code here, I'm gonna order the edges in this graph.
What do you mean order?
I'm assuming there's an order on the edges.
Sure, yeah.
which has to be, there has to be a local order for each vertex to know which string to get from the edges that look at it. So I'm assuming we have a global order, so we have n bits that correspond to the n values that you put on each edge. So is the code the set of all those strings that when I plug it onto this graph?
Yeah, so it's a set of all strings which correspond to like where every bit corresponds to an edge, where if you take the restriction to every vertex, it belongs to the base code. Yeah.
So I still have trouble with the same question that Raphael asked of picturing why removing one of those vertices doesn't just result. It lets me now choose any values for 3 bits.
Oh, no, so Eric, I think I know why, if I may. Yeah, now I understand what region. So once you remove those, like those constraints alone, right? Like you go to a bigger space, and now you could have like a different assignment to all the edges, to all the other edges that are still in the constraint, right? And they satisfy all the other constraints. But these are completely different from any code word that you previously had because you're in a bigger space.
Okay.
Yeah.
Good.
Yeah.
Thank you.
Okay. Any other questions? It's okay. Yeah, so I guess you'd hope to, yeah, so I guess like, so there's some additional structure that we need in order for us to get sort of this robust local testability. And that's precisely what high dimensional expanders are going to give us. So maybe let me tell you sort of what these are. So I guess so before we had these sort of like one complexes, we had edges and vertices, right? So now what if we actually lift this to higher dimensions? So instead of vertices and edges, now we also have triangles or maybe tetrahedrons and so on. And so in particular, we have a simplicial complex. For today, let's just say dimension 2, just because I can draw 2 dimensions. It's hard for me to draw higher than that. And then analysis should be basically the same. So let's say you have a special complex of dimension 2, downward closed. So if you have a triangle, then all the edges and all the vertices are also contained in your simplex. And we can use this notation xi, which would denote sets of size I plus 1. So x0 will be all the vertices, x1 will be all the edges, x2 will be all the triangles. And okay, so expanders, like one-dimensional expanders, like they should mimic sort of the complete graph in terms of expansion properties. Like these 2-dimensional expanders, they should mimic the complete complex, but it should be sparse. So every vertex, we want them to be contained in constantly many faces, but it should sort of have the same connectedness and same like expansion properties as like, I guess the complete complex would be. It's actually sort of this connectiveness that will give you, that makes these things hard to construct. So it's interesting because I guess one-dimensional expanders, the random graph is a good expander. These high-dimensional expanders is no longer the case. If you take a random complex, these things will be kind of too disjoint. Like, yeah, so then they actually won't give you the desired connectivity that you need for the local structure to have any meaning. So it's actually a pretty big challenge to construct like new high-dimensional expanders that are, I think we only really have 2 that are like useful for us for today, for instance.
The pretty complex means that they cannot just share a point, they have to share an edge. The triangles?
Like
how's a complex different from a hypergraph?
Yeah, so it's just, you can think of it as like a hypergraph where you have sets of size 3 and then sets of size 2 and sets of size 1. And every time you have a set of size 3, then sets of size 2 contained in it should also belong to it. And every time you have a set of size 1, you should also like contained inside a set of size 3 should also belong to it. I guess like a simplicial complex is restricted to the case where you have like, okay, I guess like maybe it's like the dimension of the simplicial complex kind of determines the sizes of your sets in your hypergraph.
I vaguely recall a definition where you actually need to be able to glue the triangles together in an order and not just at a point, but maybe not.
I think for us, it doesn't quite matter.
Okay, fine, I'll treat it as a hypergraph. That's fine.
Okay. Okay, so how do you define codes on these things?
Sorry.
Yeah.
So graph theoretically, how do these things look? You are still talking about graphs, no? Or are they becoming a actual graph?
It's actually becoming sort of a hypergraph in some sense. It's like, I think, for me, it's easier to think of it as a simplicial complex. Like it's really this like 2-dimensional object as opposed to a 1-dimensional object now.
Okay, got And what does it mean that it is approximating a two-dimensional plane?
Yeah, man, I took it out of the slide because I thought it was a little not useful. Yeah, so I guess like you want, so you wanted to mimic the complete complex. So there's sort of two things that are necessary here. One is that like it should be very expanding, right? So if you take like a walk from like maybe face to edge to face, then this thing should like kind of expand very well. And you know, the walk should be good. The second thing is like the complete complex is very connected, right? So locally, if you have any vertex, like all the things surrounding it, the edges should all kind of like be connected. And so that's the second property that you're going to need. So maybe very vague, but hopefully that's okay.
Sure, I don't know the reason why the random complex does not
Yeah, because of the connectivity issue. You take a random set of triangles, and you look at a single vertex, actually like the sort of like the triangles surrounding it are actually going to be very disconnected because it's very sparse, right? So you can't hope. Okay, I guess formally what you want to say is you look at the triangles around it and you look at like the edges sort of opposite of the triangle, and you want to see these things form like a one-dimensional graph that is a good expander, and in particular it should be connected. But it can't be, it's normal, like if you take a random hypergraph or a random complex, it won't be connected. Well, thank you for all the questions. Okay, so how do we define codes on these things? So before we put bits on edges, now we can put bits on faces. Okay, so before we had constraints at vertices looking at the neighboring edges, now we're going to kind of move everything one dimension up. So you can look at every edge and look at all the neighboring faces. And you want a local view at each edge, so of all the faces surrounding it should belong to some like edge code, which we can call CE. Okay. Okay. And then from this, so this defines your code. But then maybe a useful terminology we're going to use is like the vertex view. So in particular, if you take a vertex and you look at all the faces surrounding it, this constitutes a vertex code. And the vertex code, like these faces should satisfy the property that every edge, all the faces surrounding it, should lie in your vertex, in your edge code. I'm just using the terminology. I'm just saying like for every vertex, you have this like local view of all the neighboring faces, and these faces, if it's in the code, should be like satisfy all your edges. Okay, and now maybe you can ask the following question. What if we, would use a local test, which is as follows. We pick a random vertex, and then we check if the local view at the vertex, so all the faces surrounding it, is in the vertex code.
You're just picking a vertex, looking at the edges that touch it, and then just taking if all those edges are in the edge code.
Wait, sorry, what?
You're picking a random vertex, you look at all the edges that are incident to that vertex, and then you check if all of these are in your edge code.
No, there's only bits on the faces.
Yeah, but so you check the constraint at every edge. Is that true?
Yeah. So your code is also the bits that satisfy all the faces surrounding your vertex that satisfy every possible edge constraint touching that vertex. Yeah. Okay, so the local test could be choose a vertex and look at the surrounding faces. And I guess like one reason why maybe this has, like, so before in our one-dimensional expander, we said there's not enough structure, we can't necessarily argue robust testability. Okay, so maybe the hope here is that since now you're looking at like a collection of edges, right? And these are all related in some way around this vertex. Maybe there's some more structure that you have gained that will kind of enforce that the attack we had earlier won't work anymore. Okay. So let's try to understand whether this local test will work. Actually, instead of talking about this local test, let's talk about a different kind of test called agreement testability or agreement testing. So this is sort of like going to be you should kind of simulate it in your mind. It's not going to be quite a test you can do on the complex, but let's see what it is. So in your mind, suppose that every vertex has a local view, ZV, which is in your your vertex code. Okay. So some of these vertexes might, agree, some of them might not, but everyone has sort of like their own view of what their faces around them should be. Okay, and we say that two views will disagree if they disagree on the faces that they share. So if like one vertex says like these should be 0, 0, 1, the other one says it should be 1, 0, 0, then these disagree. Okay, and the sort of like the agreement testability definition is that if only a few edges disagree, then actually most of these vertex views have to come from some global assignment. So that's like what we want to show. And if you can show this sort of agreement test, then you can then this actually will imply that our original test where you select a vertex and you look at the faces and check if it's in your vertex code will also be robust. So this is sort of a stronger testing guarantee or property. Yeah.
So, yeah, I'm a bit confused. So you have like two vertex like A and U, but they're looking at the same bits, right?
Yeah. Yes. Yeah, so okay, so this is a mind game. So we're kind of lifting to a separate world in which now you have this game where every vertex has like a view where the view is guaranteed to be in your vertex code.
How do you construct those views from both?
Yeah, so I guess this is sort of like so let's say before we were here where all the faces had bits. Now we're moving to a different world where now we're in this different game. The different game is every vertex has a local view, which is in the vertex code. And you want to see if this sort of test where you take two vertices and compare them is robust or not. And it turns out if this test is robust, then the original one will also be.
But you still haven't defined what are these like views, right?
Yeah, so like I guess this is like sort of setup for the game. So the setup for the game is that we have a bunch of these local views. And then I guess like what we hope to show is that if they don't disagree too much, then there has to be actually come from some general global view. This sort of makes sense intuitively, at least why this seems to imply some sort of like robust testability of this code space.
I'm having but local view here that you defined is just like, I look at all the faces, like the bits on the faces that touch me, right?
Yeah.
So that's gonna be my local view. And and how is this kind of different from the same problem that we had from the just expander code, right? That let's say if I remove some set of constraints, I can also get a lot more words, and they're just not gonna agree with one local view. But as you said, like because I want a high dimension expander, I want the number of faces touching each vertex to be sparse. So I'm also not.
Yeah, so we're gonna have to analyze it. So you're right, a priori, it's not clear that we solved the issue yet, but it turns out that the HDX structure, because it's so connected in a specific way, it will actually give us the necessary connectivity to prove that the original test is actually okay.
Okay, sounds good. And the disagreement here has just to be on the local view of, because in the vertex, there's no constraint in the vertex, or there is a constraint in the vertex, right?
Yeah, the constraint of the vertex, each vertex arises from all the edges surrounding it.
So it's just that, okay, I'm gonna look at, the test is gonna be look at all the edges that's surrounding it, and I'm gonna say each of these edges has a constraint, and whatever my local view has to respect all of them.
Yes.
Okay, sounds good.
It's the intuition here that what the problem was with the graphs is that I wanted to have this kind of same agreement idea, but I couldn't because for any two vertices, the only thing they can share is this one edge. That's it. Whereas now between any two vertices, we kind of have a lot more structure about what they could agree with.
Yeah, I think that's some good intuition. Yeah.
I see.
Oh yeah, my question was about like some parameters. So we're thinking, so the number of faces now is sparse. So each edge, we can think will be in some constantly many faces, right? How many faces will each vertex be? Is it still constant?
So every vertex is contained in constantly many edges, which are containing constantly many faces. Okay. So each like local view should be constantly sized. So maybe let's try to prove agreement testability and see what happens. So we have this mind game, right? So each vertex has sort of a local vertex view. And we would like to find some sort of global assignment that will explain all of these local views. And how do we find this thing? So what we can do is, so we start with these local views. And let's do the following operation. Okay, so both are the sort of disagreeing edges. So like ZV3 and ZV1 don't agree on their shared faces. And we can play the following game, or like do the following algorithm. So we can find a vertex which has some number of disagreeing edges away from it. And if there exists some sort of like new local view, new vertex view that will decrease the number of red edges, we're going to change it to that new vertex view. So yeah, so this one has 4 red edges now, and maybe if we change it, now we have 2, so we make this change and we can keep going. And so at every point in time, the number of red edges will decrease. And then at some point in time, this algorithm will terminate, and either there will be no red edges left or there'll be many. And the question is then like, what can we say in either case? So in the first case, if all local views agree, so there are no red edges left, then we have found a nearby code word. The distance to this code word is sort of bounded by the number of toggles you've made, which is the number of red edges to start with. So we found this sort of global view that will explain most of the local views, and so we're happy. The question then is, what happens if when this algorithm terminates, you actually have many disagreeing, still have many disagreements. And so I guess in this case, we have to show that there actually have to be many disagreements. It's not possible that there's only a few disagreements and you get stuck. Okay.
I missed it again. When is an edge red?
An edge is red if this edge is red if this and this disagree.
What do you mean by disagree?
Disagree means yeah, so if these two vertices have like disagreeing views on these like shared faces, then we say disagrees.
If the faces are fixed, how can I help?
Okay, good. Yeah, so we're sort of in this new world, we're in the mind game where every vertex has like a local view belonging to the vertex code. So this is like kind of departing from reality a bit. You have this like it's like a game where every vertex is like, this is what I think is true. And like there might be clashes. And your hope is that eventually you can actually resolve all these clashes to some global view that will explain everything. Okay, it is okay. So I guess the thing left to do is to show that there actually have to be too many disagreements to start. Otherwise this algorithm should actually end up in the everyone's happy sort of state. Okay, so how do we do that? So to do this, we're going to analyze the following random walk. The walk is as follows. We're going to start with an edge. We're going to pick one of the 2 vertices surrounding it. Let's say we pick this one. We're going to pick a random triangle touching this vertex, and we're going to like jump to the opposite edge. So that's a random walk we're going to look at. Turns out this walk is expanding. It's just a very expanding walk that you can show. And then I guess the hope then is to show that if you start out with a bad edge here, then once you take one step of this random walk, you still end up with like a bad, like disagreed edge with pretty high probability. If you can show that, then what happens is, okay, so if you can show that, then if the set of red edges was actually very small to begin with, this expanding walk, because it's such a good expander, should actually lead a set with very high probability, which would contradict like sort of the probability of staying in the bad set to be very good. So then this actually the entire the number of red edges actually has to be quite large. Yeah.
What would be the initial views? So we are given a codeword, and then how do we assign the initial local views to each vertex?
Yeah, so let's take a step aside from the original view. We're going to go to this like separate like world in which every vertex is going to have like a vertex view inside the vertex code. Yeah. So each of these vertices might disagree on, it might correspond to reality, like they actually might clash, but every vertex has sort of a vote on what they think the faces around it should be. And the goal is like, hopefully you can resolve all of these clashes and find a global assignment that's kind of nearby.
What is the initial view?
Yeah, so it's a setup for a game, like it's just a setup. So yeah, so if you want to go through like the original yeah, so I guess like in the original test, if you have a code word surrounding, like if the view around a vertex is a code word, you just send that code word to be the vertex view. If it's not a code word, you can send it to be the all zero string or something. It's okay, like, so our goal is to show that if you start with a bad edge and then you take this walk by one step, you'll still end up with a bad edge with very high probability. Okay. So here we want to assume, let's assume for now that the vertex code surrounding each vertex is agreement testable in itself. So now what we can do is, let's start with any vertex that has a large number of bad edges surrounding it. This you can find because of the distance and like the expansion properties of the local view over the local graph. And now starting with this vertex, let's look at all the edges sort of like that are like away from this vertex by like on the opposite side of a triangle. So the goal is to show that many of these edges will also be bad. Okay, how do we show this? Well, this is where we use the vertex code is agreement testable. So if there aren't that many edges here that are bad, then by agreement testability, that means that there is some local view for this vertex here that actually has very few disagreements to all of these like yellow edges. So then you could actually change this to a better vertex view that has fewer disagreements, which would be a contradiction because we assume that the algorithm terminated and that there's no more like local adjustments you can make to make things better. Okay, so then there have to be many red edges on these sort of like opposite sides of these triangles. And now if you take a random edge that touches the V, and then you do this walk where you jump to V and then you jump to a sort of opposite edge, then you'll still end up in the bad side with pretty high probability. Is that okay, or?
Sorry, yeah, can you go again? I think I get the part of the yellow edges. So what you're saying is that by the time the algorithm stopped, you cannot have many of those yellow edges. That's what you like. Not many of them have to be bad, actually.
That's what we want to show, yeah.
That's what you want to show.
Yeah, if you can show that, then the random walk I described earlier will have to kind of go from bad edge to bad edge with high probability. And that's good for us because then.
Oh, I see. So you haven't shown that yet.
Not yet. We're just looking at the yellow edges.
Okay.
Okay, so how do you show that? Okay, so the way you show that is you look at all these yellow edges. If there aren't many that are bad,
Right.
so actually most of these vertices agree, then by agreement testability of the vertex code, you actually have to find a better view here that will have fewer disagreements to the surrounding vertices.
Right, and why? Yeah, and why does the agreement testability shows you that you could have changed CV?
It's just a definition of agreement testability. So agreement testability says if there's few disagreements with all these yellow edges, then there is some like sort of global view, in this case just this vertex view that explains all of them.
Oh, I see.
Or like
That
most of
is
them.
the assumption. Okay,
Yeah, that's
sure.
assumption. We'll have to come back to this.
Okay.
Yeah, so once you have that, now you have many edges that like these kind that are opposite of the vertex V that are bad, and then your random walk now goes from bad to bad with high probability. Okay. Is that good? Okay. So yeah, so okay, so I guess assumption here is we kind of assume this vertex code is agreement testable, and then using the expansion properties of the entire HDX, now you can get sort of like global local testability. I guess so like this, so yeah, so what have we shown so far? Okay, so what we've shown so far is the result on a few previous works that show that if you have this agreement testable vertex code, and then you have this like expansion structure of the HDX, then you can actually get an OTC. Okay, and so we'd like to instantiate this paradigm.
Can I ask a super question before
Yeah,
you do that?
yeah.
It feels to me that what you're doing is you're taking a code on an expander, but originally our test was, you pick a vertex and then you check whether all these edges, originally you had like a constraint on every vertex and you're like, okay, I'll pick a vertex and I'll check if all these edges satisfy this constraint. But now it seems to me that you're doing the same thing, but instead of checking on one vertex, you're just saying, I'm going to pick a few vertices and I'm going to check if all the edges, if all of these constraints are simultaneously satisfied. Is that true? Because
that's sort of true, yeah. I think the important thing is that the new edges here have much more structure than maybe you would get in a generic.
You're just picking which subset of vertices you pick to do the checks, you're just picking those non-trivially.
Yeah, and also the structure of the graph has to be non-trivial also, just because you need these things to check each other very well. Whereas if you take it as like a, suppose a generic expander, you might not have that. Yeah. So, okay, what I've done so far is showing you this formula. If you have the agreement testable vertex code and you have an HDX, and these things are compatible, so the vertex code is compatible with like the HDX, then you get LTC. Yeah, so we like to instantiate this paradigm. How can we do that? Well, for the HDX, we only really have like, I think 2 options. There's the Kaufman and Oppenheim coset construction, and then the Ramanujan complexes. At least for constant degree. I think for constant degree HDXs, these are like the only 2 that we have. And so I guess there aren't that many options for these HDXs, and I guess we'd have to instantiate with one of the 2. So for us, we chose the Kaufman Oppenheim construction. Okay, so I'm just going to go on now to show you a bit about this this vertex code. Okay, so let me tell you maybe what our global code is. So I won't tell you what the Kaufman Oppenheim like HDX is, but okay, so it is HDX. So we have these triangles, have edges, vertices, and okay, every edge is going to have Q faces attached to it, where Q is like maybe a power of a prime. And instead of this, let's look at symbols from FQ on each of the faces. So what is the code we want to put on each edge? We're going to put a Reed-Solomon code on the faces around each edge. Okay, what is Reed-Solomon, for those of you who don't know? So the Reed-Solomon code is a set of code words. Each code word corresponds to a polynomial. So for us, we're going to be looking at polynomials of degree at most d. And then for this polynomial, you then look at maybe all the points in FQ, and you evaluate f on each of the points. And so we'll give you sort of like a series of code words, each one corresponding to polynomial. Okay. And so that's our code. So I've told you what the edge constraints are, right? And if you know what the Kaufman Oppenheim construction is, then you know what the code is. Okay, I also want to mention that there is a way that you can sort of embed these faces into like FQ to the M. So that the faces are actually points in FQ to the M. And like the points on each edge, like the faces surrounding each edge, correspond to like a line in FQ to them. So I guess another way to say what I'm trying to say is like this code is actually another way to see this code is as a sparsification of the Reed-Muller code. So if you know what the Reed-Muller code is, it's basically the same as the Reed-Solomon code, but it's like multi-dimensional. So it's like M variant instead of just 1 variant. And it's known that like the Reed-Muller code is actually, it's locally testable. The way you do it is you select a line, you check all the points on the line, and you see if it lies on, low degree polynomial. Yeah, and so, but for the Reed-Muller code, like for the local testability, you actually need to pick a line in every direction, or like you actually need to choose a line in any direction. For us, we're now in this like high dimensional space still, but our lines are actually very sparse. There's only like a few lines per point that you can possibly choose. Okay, cool. So now I just want to tell you maybe what the vertex code looks like, just to give you a picture. So here's what our vertex code is going to look like. So for each vertex, there's going to be a bunch of faces surrounding it. The faces will sort of lie in this cube. So remember before I told you each triangle now embeds into like a point in like a single point. So each of the q to the q cubed points will be a face surrounding this vertex. And so each of these points should be an element in FQ. Okay, and then what are the edge constraints? So there's 2 types of edges. The first type is going to be of the following form. They're going to be just horizontal like lines in the x direction. So for every fixed y and z, the sort of the edge, like the line going in x direction should lie in a Reed-Solomon code. And then okay, for the y direction, it's a little different. So there's this sort of like skew y thing going on. So if you fix like a x and a z coordinate, so a and c, then you take the sort of like twisted lines in each direction. You get you want to show that those also are on a Reed-Solomon code. So I guess in particular, if x is 0, these things are horizontal. X is 1, they're like kind of more slanted, and they kind of like turn as the code goes on. Okay. So so what's the agreement test we want to show? So in the agreement test, we have like a local view for each each edge. So here, what do we have? We have 2 types of views. we have these red views, the flat ones. So we can maybe write like a global assignment x, y, z of these things, and it has a property that for every like fixed y and z, the code in the x direction should be on a read element code. And similarly for the y direction, we can write this like y, x, y, z, which has to satisfy the property that for all these green lines, the points have to lie in a read element code. Okay, so what is the agreement test? Okay, so the agreement test is you literally just pick two of these, so one red and one green line, and you want to, and the intersect on a point, and you test if these two things are equal on that point. That's the agreement test.
Sorry, and the points, sorry, and for the vertex code, so they should be like the view of the vertex. But in the for each vertex, what is the guarantee? How many facets are gonna be around this code? Sorry.
Yeah, there's q cubed faces around
So it's
it.
gonna be cubed faces around this, and each of them is a point of this.
Exactly.
Oh, okay, sorry. Okay.
Yeah.
Sounds good.
Yeah, and it just turns out when you plug it into this like KO complex, these are the sort of the edges that you get out of it.
Okay.
So okay, the agreement test is you pick a red line and pick a green line, and you check that they're equal on the shared point. And the theorem we were able to show is that if yeah, so basically it's this test where you take one red line and one green line and you check if they're equal. This agreement test is robust. And this is really like the core like theorem of our paper, and yeah. Okay. Okay, so I guess in conclusion, so there's this paradigm that we knew existed. So we knew that there was agreement testable base code in HDX and you get LTC. What we did is we analyzed this base code. We were able to show it's agreement testable. And so now if you plug it in, you get LTC. So okay, some future directions, some open questions. Okay, so I guess first I mentioned that, okay, so we have constant distance, we have constant locality. One thing we don't have is constant rate. Don't know how to analyze this. Right now, all of our techniques for analyzing rate are of the form, you count constraints basically. Like you count number of bits, you count number of constraints you have, you subtract them. If it's positive, you have some rate. If you don't, then you don't know. Okay, so we get some rate. Like we have like, you know, there are code words because it embeds in sort of into read-muller, or read-muller is kind of contained in this code space. But like ideally we could, you know, do a better analysis of the rate. It would be really interesting if we could get methods for analyzing rate that aren't just constraint counting. That would be really amazing. Another question, I guess, in the direction of like PCPs is our code has this like multiplication property, which is like potentially useful for getting PCPs. But like ideally we'd also be able to kind of like create some form of sum check or some sort of protocol on these codes that would make them even more useful for PCPs. I guess if you know what PCPs are constructed, they're like, you know, read-muller code plus like a sum check, and then you unroll the sum check. So we sort of need some additional structure, I guess, or some additional thing compatible with these codes to turn them into PCPs. And I guess the final question I just wanted to highlight is like, I guess in like recent development in quantum codes, there's a lot of interest in these like high dimensional expanders or like just like complexes related to quantum codes. And so I guess one question that I haven't looked into very much is whether or not these will give you some sort of good quantum code. Yeah, that's all I wanted to say.
Thank you. Apart from all the questions, if anyone has more questions for Rachel.
Can you tell us a bit more about the connection to PCP? I think you mentioned Lapche, but so you want a PCP, let's say, with order n size pro, and you want it to be 3, like you want to only query 3 points in the PCP, and that's
well, that would be ideal, yeah, but constant would be interesting. I think even I want to say even like polylog is not known. I think any sort of constantly sized PCP is not known.
But
like
polylog is small, yes.
And polylog, yeah, I think so.
Okay. And why do we want those PCPs?
I guess one application, I think it gives you better like hardness approximation results, for instance.
Like what, for example?
Okay, so I don't know too much about this literature, but like I guess PCPs are related to many areas. One that I know people are like especially interested in is like hardness approximation. And so I think like someone told me there were like, you know, real implications of like, you know, linear size PCPs to these things, but I don't know exactly what they are.
Got it. And for those applications, you need them to also be locally decodable, like.
So I mean, just a key like component in PCPs is like these locally testable codes.
Okay.
So like, I guess, you know, as a starting point to get these things, you might want like good locally testable codes.
More questions? If not, let's take Rich look at it.